Great. So for our next portion of the Groundwater Open House Day 1, we're going to jump into our next session of contaminants. I'd like to introduce our first speaker for the first talk, Giovanna. Is Giovanna? There she is. So she'll be giving our first talk, and then we'll jump into a discussion panel. So Giovanna, you can take it away whenever you're ready.
And just as she comes, if we can have the lights in the house down to where they were before.
Okay. Hello, my name is Giovanna. I am postdoctoral fellow in Ecohydrology Research Group at University of Waterloo, and today I will present our recent work, Beyond Phosphorus, Salinization Amplifies Eutrophication Symptoms in an Urban Lake. During today's presentation, I will actually try to explain how we establish novel link between two huge water quality problems, eutrophication symptoms and salinization, that are before this research considered separately. As many of you already know, changes in land use and land cover have brought many water quality issues. If we think about water quality problems overall, eutrophication is one of the huge water quality problems for many decades. Eutrophication itself is often related to agricultural development and access of nutrients from the watershed to receiving water bodies, such as lakes or rivers. For freshwater ecosystems, phosphorus is considered to be a limiting nutrient, which means that it's often responsible for eutrophication and eutrophication symptoms, which includes internal phosphorus loadings and anoxic or hypoxic conditions. Internal phosphorus loadings means that phosphorus is remobilized from sediments, while anoxia and hypoxia are conditions of oxygen depletion. The other huge water quality problem that is also very well recognized, and it's a problem for many decades, is actually salinization. In past decades, cold temperate urban regions represent regions that are at high risk due to road salt application on imperviousness, because salt here is used to maintain winter conditions and keep people safe. We conducted the research on Lake Wilcox, which is a small lake in Greater Toronto metropolitan area in Canada. This is Kettle Lake, and it belongs to cold temperate regions, which means that during the winter, road salt is used to maintain road conditions. In general, this research site is very interesting because more than 20 years of water chemistry data were accessible, and also this watershed has undergone significant change in land use cover since the beginning of the 20th century. At the beginning, the watershed was forested, then it switched to agricultural, and nowadays this is an urban watershed. The most significant increase in urbanization of Lake Wilcox watershed happened after 1990s, and we actually observed increasing impervious cover, which is actually proxy for urbanization, from around 25 to more than 60%, which is urbanization of Lake Wilcox watershed nowadays. Even before this period of significant increase in urbanization, Lake Wilcox water suffered from harmful algal bloom and also anoxic and hypoxic conditions. And that is the reason why the city implemented stormwater management ponds in 2000s. In that way, they actually wanted to reduce the amount of phosphorus that is coming from the watershed to the lake, and that is called external phosphorus loads. Because phosphorus is a limiting nutrient and it's often blamed for all those water quality deterioration problems. As you can see from the bottom graph, they actually succeed to reduce the amount of phosphorus external loads. However, the Lake Wilcox didn't improve its water quality and it still remains in its eutrophic state. To see why is that happening and why Lake Wilcox hasn't improved its eutrophic state, we analyzed more than 20 years of water chemistry data, and we found that together with increasing impervious cover, salinity of the lake also increased. Salinity here is observed and represented through increasing in chloride concentration, and the reason why salinity increased is salt application on accelerated imperviousness. So in this research, we really wanted to see to what extent and whether eutrophication symptoms and salinization are linked, since those two separately are very well-known water quality problems, and Lake Wilcox suffer from both of them. When salt is applied in the watershed, one part will be flushed to the lake, and exactly that salt will actually lead to increasing water salinity. And I showed that in one of the previous slides. In addition to that, water density also can increase, and that can lead that vertical mixing is disturbed. To see whether and to what extent lake mixing of the Lake Wilcox is disturbed, we use the Brunt-Vasala frequency, and Brunt-Vasala frequency is actually proxy for certification. If the values of Brunt-Vasala frequency are higher, that means that for lake is harder to mix and to overturn because the thermal stratification is stronger. On this graph here, you actually can see that nowadays values of Brunt-Vasala frequency are significantly higher than in the past, which means that nowadays for lake is harder to mix and to overturn. When for lake is harder to mix, for oxygen it's harder to reach the bottom of the lake. That's why from the year around 2005, we observed those prolonged periods of anoxic conditions that are in this heat map represented in blue color. Before that, we had normal mixing regimes for dimictic lake. What actually happened here is that salt that is flushed to the lake increased the water density, and once when water density increased, for oxygen was harder to reach the bottom of the lake, and also mixing of the lake was disturbed. All lakes in Northern Hemisphere, or most of them, mixes 2 times per year, during the spring and during the fall. Those mixing events are very important for lake health because during that time we have fully oxygenated water column. However, if we have denser water, mixing can be delayed. So between spring and between the fall, we have period when the water column is stable, which is actually period of stratification. And during that period, we have less and less oxygen at the bottom of the lake. So if we have those denser water and prolonged mixing during the fall, if the mixing actually happens later, that means that lake water will, for most of the year, in its hypoxic or anoxic conditions. Those hypoxic and anoxic conditions that can happen almost the entire year are very worrisome, but also they can contribute to increased contribution of phosphorus remobilization from the sediments or internal phosphorus loadings. That is actually what we observed in Lake Wilcox through increased ratio between dissolved phosphorus and the total phosphorus, as you can see from this bottom graph. So during those anoxic conditions that are here prolonged and caused by salinization, in addition to external phosphorus loadings or phosphorus that is coming to the lake from the watershed, we also have contribution of internal phosphorus loadings, which is also very worrisome. So increasing in both eutrophication symptoms, hypoxia, anoxia, or internal phosphorus loadings are happening here despite the fact that total phosphorus external loads to the lake declined. So despite decrease in external phosphorus loadings, lake exhibits water quality trends that are typically associated with nutrient enrichment. So in this research, although for many decades phosphorus has been blamed for all those eutrophication symptoms, we really show that salinity and not external phosphorus loadings amplifies those eutrophication symptoms. Furthermore, we wanted to see what is happening with the road salt when it's applied in the watershed. To do that, we developed mass balance modeling approach, and something which we observed is that with increasing impervious cover, more salt is directly flushed to the lake and less is retained in the watershed. On this bottom graph, you can see that with increasing imperviousness, we have less and less watershed retention. However, during this period observation, it's already a huge amount of salt that is retained in the watershed, probably in soil and groundwater, and exactly that salt can behave as an ongoing source for contamination for both aquifers and also downstream ecosystems, such as, for example, in our case, Lake Ontario. The salt that is accumulated in the watershed is actually represents salt legacies. And that is something that represents a huge problem for salinization problem. Because we have that salt that is accumulated in the watershed, even in some imaginary scenario, if we stop to use the road salt as from today, we are still going to have salinization problems because that salt will eventually be flushed to lakes and also groundwater, and we need many, many years that we actually don't have that problem. The mass balance model that we developed also could be a useful tool to see what is going to happen with the lake water quality in terms of salinization if we continue to use the salt as today, but also what can happen with the lake quality in terms of salinization if we reduce amount of the salt that is applied in the watershed. Something which is also very worrisome and very clear from this graph is that Lake Wilcox already reached federal chronic chloride limit for aquatic ecosystem health. And also we need to do a huge reduction of the road salt that we go below this threshold. Also, this model that we developed here could be a useful tool for other freshwater ecosystems, such as lakes or ponds. Since in this research overall, we established another link between two huge water quality problems, eutrophication symptoms and salinization, we really wanted to see to what extent we can apply our conclusions for more lakes globally. To do that, we started with lakes of North America that experience increasing salinity due to use of the road salt on impervious cover. So something which is also common for all those lakes and also our case study is that best management practices are implemented in order to reduce the amount of phosphorus external loadings or phosphorus from the watershed to the lakes. They succeed to do that, however, all those lakes remain in their eutrophic state. Furthermore, we analyzed the data for all those lakes and we found that in addition to increasing salinity, stratification of the lake also increased, and we also further observed that we have less and less oxygen in hypolimnium of those lakes and that we have greater contribution of internal phosphorus loadings. All those trends are the same as for our case study or very similar, so we actually concluded that for lakes of North America, salinity and not external phosphorus loadings amplifies those eutrophication symptoms. And in this research, where we established another link between eutrophication symptoms and salinization, we also wanted to point out that salt pollution is a global issue, that salinization is a huge threat to urban water bodies, that in cold regions more urbanization means more road salt, that salinization can strengthen the lake stratification and further lead to intensifying internal phosphorus loadings and overall disturbances of nitrogen cycle. And also we wanted to emphasize that changes in stormwater and de-icing management practices are needed if we want to improve, but also to preserve the water quality of our freshwater bodies, including wetlands, ponds, reservoirs, and lakes. And if we really want to do something about persistent eutrophication symptoms, we really need to address salinization issues in addition to phosphorus, since here we really show that it's not just phosphorus important, but the salinity could be as equal as important. The findings that I presented today are published in few research papers. And also we wrote many outreach articles that could be very useful tool that broad public get informed in terms of road salt problems and salinization problems overall. And from all those articles, I would like to distinguish the articles from the conversation that has brought a lot of attention to our work. With this, I would like to thank you for listening, and I would like to thank all people who contributed to this work.